identity matrix means in main diagonal we have element 1, okay, that is clear, and other are 0, other all are 0. That is a fix, right, and identity matrix. Now this is our matrix A, this is A transpose. So that means what? Whatever the first row, that is exactly the first column. When you multiplication of these two matrices, the first of all we have to multiply first row with the first column, right? And when you multiply, the multiplication and summation of that first row of the first matrix and this first column of the second matrix, that will become definitely 1, okay. That means what? These vectors are orthonormal, because the multiplication of with the same vector with the same row you will get 1, and other, when you multiply other you will get 0, okay. So now you can understand that the correct answer is orthonormal. Now next question, question 6. In the first question, part A, our transformation T from R2 to R2 be a linear transformation defined by T of xy is equal to yx, then it is 1 1 onto, the options are 1 1, then onto both, that means 1 1 and onto both, or neither. Neither means none of this. Now this is our Euclidean linear transformation. T of xy is equal to yx. So the standard matrix of this transformation is 0 1 and 1 0, right? Okay, that you can understand that how we find the standard matrix of any Euclidean linear transformation. Our transformation is from R2 to R2. So the standard matrix for this linear transformation, that is also 2 cross 2. The first coordinate is y. So in the first coordinate, the coefficient of x and y, that is 0 1. So that's why the first row is 0 1 and the second row is 1 0. Now this matrix is a determinant -1, non-zero determinant, right? So this is, so that's why this is 1 1 and onto both. Okay, onto to understand that the given transformation is onto is quite easy, because for any yx belongs to R2 we can find xy such that T of xy is equal to yx. That is the only reason, right? The onto means for any element from the codomain there exists such at least one element from the domain such that the image of that element is equal to that element, okay. So suppose we are taking y belongs to the codomain. So for any y belongs to R2, for any this is something in general cases, our transformation T from U to V, capital U to V, the meaning of one-oneness and onto-ness, right? What we have to do, one-oneness means our transformation T, our function T from U to V, capital U to capital V, where U and V both are vector space. So if you want to check that our transformation is 1 1 and onto or not, so for that for 1 1 what we have to do, T of x is equal to T of y, right? And try to prove that x is equal to y. In other words, if for x not equal to y, we have to prove that T of x not equal to T of y. So in that case the transformation is 1 1. Now for onto, what we have to do, our transformation T from U to V. So for any y belongs to V, there exists x belongs to U such that T of x is equal to y. If this thing happen, then we can say that our transformation is 1 1 and onto both. But there are some theorem that to prove that 1 1ness is quite easily, because if our standard matrix for a linear transformation is non-zero, have a determinant non-zero, then that transformation is always 1 1 and onto both. So in that case the same situation happen here. Our standard matrix is 0 1 1 0 for this linear transformation, and that's why the determinant is -1, and that's why this our transformation is 1 1 and onto both. So the correct answer is both. Next question 7. Let T from R3 to R3 be a linear transformation defined by T of x y z is equal to y z 0. Then the dimension of range of T is 0, 1, 2, 3. Right? The choices are 0, 1, 2 and 3. The correct answer is 2. Why correct answer is 2? Because the standard, again you can see the standard matrix for this given linear transformation is what? 3 cross 3 matrix. First row is 0 1 0, the second row is 0 0 1 and the third row is 0 0 0. The given the standard matrix is itself in row echelon form matrix, right? You don't need to convert into a row echelon form matrix. This is in fact this is a projection, right? Not exactly the projection, but you can see T of x y z is equal to y z 0. So the first coordinate is y. That so the coefficient of x y z in the first coordinate is 0 0 0 1 0. So that's why the first row is 0 1 0, and the coefficient of in the second coordinate of x y z, that is 0 0 1. So that's why the second row is 0 0 1, and the coefficient of x y z in the last coordinate, third coordinate, that is 0 0 0. So that's why the third row is 0 0 0. So our standard matrix is 0 1 0 0 0 1 and 0 0 0, right? And that matrix is also in row echelon form matrix. How many non-zero rows in our standard matrix? 2. So that's why the dimension of range of T is 2. So this question number 1A, first part A complete. Now question number B, there are 7 questions. Now another 7 questions. Question 1B, if norm u plus v square, that is equal to norm u square plus norm v square, then u and v are A parallel, B perpendicular, C dependent, or D none of this. The answer is perpendicular. Why? Because we know that norm u square is equal to, we can write down inner product u with u. So similarly you can write down norm u plus v whole square, that is equal to inner product u plus v with inner product u plus v, right? And when we simplify that term, finally you will get norm u square plus 2 inner product uv plus norm v square. That means what? The middle term becomes 0. 2 inner product uv is equal to 0. That means inner product uv is equal to 0. And that thing happen only when u and v both are orthogonal. That means what? That two are perpendicular, right? Orthogonal means that two vectors are perpendicular to each other. So that's why the correct answer is, if norm u plus v whole square, that is equal to norm u square plus norm v square, then u and v both are perpendicular to each other. Next question B 2. This is a theorem. Then norm u plus v whole square minus norm u minus v whole square, that is 4 inner product uv, right? That is one result which is all given in the books of the second semester. Okay, you can also prove it if you want to prove, because norm u plus v whole square, that is norm u square plus norm v square plus 2 inner product uv minus, this is also norm u square plus norm v square minus 2 inner product uv. So finally you will get 2 inner product uv minus 2 inner product uv. So finally you will get 4 inner product uv. Okay, so that's why the correct answer is D, 4 inner product uv. Now let T from R3 to R3 be a 1 1 linear transformation, then the dimension of kernel of T is, now for 1 1 linear transformation there is one important theorem for 1 1 linear transformation. If our transformation is 1 1, then kernel of T is always singleton theta, where theta is a 0 element of the domain, right? So in that case, if kernel of T is equal to singleton theta, then definitely dimension of the kernel of T is equal to 0, because there is no non-zero vector in the set. So that's why the dimension of the kernel of T is equal to 0. That is quite easy to solve. The next question, question 4. These two examples are quite similar, question 4 and 5. That A is equal to 2, 1, 2, 3. Then the eigenvalues of A square are, options are 1, 2, 1, 4, 1, 6 and 1, 16. Now first of all we want to find the eigenvalue of A, right? In 2 cross 2 matrix, to find out the characteristic equation, what we have to do? Lambda square minus trace of A. Trace of A means the sum of the diagonal elements. Now this is our diagonal elements 2, 3. So sum of that diagonal elements is 5. So lambda square minus 5 lambda plus determinant. Now what is the determinant? 6 minus 2, that is 4. So what is our characteristic equation? Lambda square minus 5 lambda plus 4, that is equal to 0, right? Lambda square minus 5 lambda plus 4 is equal to 0. That is the characteristic equation for this 2 cross 2 matrix. And factorize that equation, you will get lambda minus 4 and lambda minus 1. So the value of lambda is 1 and 4. So the eigenvalue of the given matrix is 1 and 4, right? Now there is one important theorem that if lambda is an eigenvalue of A, then lambda raised to k is an eigenvalue of A raised to k. So similarly, if you want to find out the eigenvalues of A square, just we have to square of the eigenvalues of A. So 1 and 4 are the eigenvalues of A, right? So 1 square and 4 square, so that is 1 and 16. These two are eigenvalues of A square. So the correct answer is 1, 16. Next question, similar type of question. If A is equal to 2, 1, 2, 3, you can see the both matrices are same, right? Then the eigenvalues of A plus 3i. Now when we add 3i in this given matrix, just 3 is add in the main diagonal entries, no other elements, right? In no other elements. So 3 plus 2, 5, 3 plus 3, 6, right? So 5, 1, 2, 6, 5, 1, 2, 6. Now again just try to understand our matrix is now, this matrix is A plus 3i is 5, 1, 2, 6, right? Okay, just try to understand. This is our matrix A, that is 2, 1, 2, 3. So what is A plus 3i? 2 plus 3 here, so that is 5, 1, okay, 2 and 6. So the characteristic equation is lambda square minus trace of A, that means 6 plus 5, 11 lambda plus determinant. What is determinant? 6 into 5, 30 minus 2, so 28 equal to 0, right? Now this is our characteristic equation. So when you factorize, this is 7 into 4, so lambda minus 7, lambda minus 4, that is equal to 0. So 4 and 7, these two are eigenvalues, correct? So the correct answer is 4 and 7. Okay, the next question, question 6. Divergence of R is R bar, that is 0, the first option is 0, 1, 2, 3, and the correct answer is 3. It's quite easy to understand. If the value of line integration f dr does not depend on path C, then f is, options are solenoidal, incompressible, irrotational, and none of this. So the correct answer is irrotational, right? So you can see in first question in this question paper we have 14 objective types of question. Each question have 1 marks, right? So this first question 1 is complete now. Next question, question 2 A. Solve the following system of equations using Gauss elimination method. We have 4 equations here. The first equation is 2x1 plus x2 plus 2x3 plus x4 is equal to 6. Second equation is 6x1 minus x2 plus 6x3 plus 12x4 is equal to 36. The third equation is 4x1 plus 3x2 plus 3x3 minus 3x4 is equal to 1, and the last equation is 2x1 plus 2x2 minus x3 plus x4 is equal to 10. And this question was asked in 5 marks in this question paper. Definitely we have to solve this question. To solve this linear system of equations we have to use augmented matrix. So you can see the first row is coming from the first equation, the coefficient of x1, x2, x3, x4, 2, 1, 2, 1, right? And then right hand side all the constants, that is 6. Okay, similarly the second row becomes 6 minus 1, 6, 12, and then 36, then 4, 3, 3, minus 3, 1, and then 2, 2, minus 1, 1, 10. Now we have to convert this matrix into a row echelon form matrix, so that's why we are multiplying first row with minus 3 and add into the second row, then multiplying first row with minus 2 and add into the third row, and then multiplying first row with minus 1 and add into the fourth row. So finally we get this augmented this matrix 2, 1, 2, 1, 6, 0, minus 4, 0, 9, 18, 0, 1, minus 1, minus 5, minus 11, and then 0, 1, minus 3, 0, 4. So in first row this is our leading entry, below that leading entry we have all 0. In second row this is our leading entry, right? So this leading entry is not 1. If we make our leading entries become 1, it's quite easy to solve other elements make 0, right? So that's why we are converting, we are interchanging second and third row. So first and fourth row are as it is. You can see the next step is